My name is Peter, and I'm from Lund, and I will talk about connectivity and various protocols.
Let's try again. We had a few technical difficulties here in the room. Peter, please start.
Okay, so we are back online. I hope we are rid of all the feedback loops by now. We continue with the context of my experiences that I'm going to share with you, and that was to provide wireless connectivity for sensor networks. Why is that not updating? Oh, there you go. It's for low power devices that can run using power harvesting. We can accept low data rates, but we do need two-way communications for actuators, firmware updates, and stuff like that. Security is, of course, imperative when we talk about modern communication of any reliable source these days. We also need cloud interoperability because devices reporting data should report it to some meaningful standardized endpoint, and AWS IoT is pretty much a de facto standard for such things. And all of this in combination means that we need some sort of IP connectivity. And to recap, this one is slow. There we go. To recap, energy requirements for radio communication, they typically depend on how much output power you need, which is a function of the range you need. The frequency plays some role in this, especially with vegetation, antennas, environment for the radio, your electronics, and the amount of data transmitted and received. And it's a known fact that many radio technologies spend more energy when the radio is listening than when actually transmitting. We'll get back to that later. Then there is overhead related to secure communication, and there are a few properties that you typically want to have when you communicate. Maybe confidentiality, that no one can eavesdrop your communication. That is more or less for free because you can do encryption without adding to the message sizes. To have integrity checks, you need something like message authentication code or integrity code, which is going to be 32 bits or more. If you go for digital signatures, you are in the range of 64 bytes and much more for RSA signatures. If you're going to do key exchange, we will spend at least 3 round trips for an authenticated key exchange, and the payload of those messages will depend on the size of your keys and your cryptographic schemes. So that brings to the question, why not just use a modem together with AWS IoT? For instance, the Sony Altair modem has pretty good power profiles, but the handshakes for TLS sessions to Amazon is not super IoT friendly. The chains there will spend like 6K bytes for the certificate chains alone. A device cannot sleep indefinitely and maintain a TLS session to Amazon. If you are absent for more than 15 minutes from Amazon, you will have to do a new handshake. And at the time we did this work, Amazon did not support the abbreviated TLS session resumptions. Looking at the LTE side for Cat M1, the TX power is most likely much greater than 100 milliamps. There are some nice power saving features in Cat M1. You can have extended DRX cycles, which means that the device does not need to be listening every 1.28 seconds, which is standard in LTE. Disconnection is a bit of an issue for a device sending small amount of data, because it is network that allows when the device can stop listening to completely disconnect the network. And that depends on the network operator settings. It can be several tens of seconds. So for a super short transmission, you have an enormous overhead just waiting to be disconnected. A new feature, I think it's in release 14, is called release assistance indication. And there the UE can, or the modem, can indicate that it wishes to be immediately disconnected. And then you can cut that down to maybe 5 seconds or so. But it's still a bit of an overhead for a short transmission. So instead of using LTE communication, we can then venture into short-range radio communication. And one of the dominant one is the 802.15.4 packet radio, which is available at the 2.4 gigahertz band or 868 sub-gigahertz. Here the TX power is going to be much lower, like 10 milliamps or so. The link bitrate at 2.4 gigahertz is 256 kilobits, and that sounds good, but it's we will see later that it's a bit of an optimistic figure. To send IP packages over this bearer, we need the 6LoWPAN to fragment and assembly IP packages. Since the link is now limited, we can think of extending it using mesh network technologies. And then we need to solve the routing in our mesh network, where we can resort to the RPL or Ripple routing protocol, which is available in 2 flavors. You can either have only the root node with knowledge to do downward routing, or you can store routing tables at each node, in which case all nodes can do downward routing. And then routing brings back to the radio on listening, and there is an amendment called E of the 802.15.4, which allows scheduling so that even a routing node can go to sleep. And there are 2 major approaches to that, either a protocol called 6-top or autonomous scheduling called Orchestra. Security on 802.15.4, according to IEEE, is based on AES with symmetric encryption and or MAC. To distribute keys for the link layer, there is an IETF protocol called CoGP, which in turn rely on security protocols, OS Core for REST security on CoAP, or Lake for doing a full authenticated key exchange. And since this is quite a few components, we looked into existing implementations for this 6-tish stack, and one of them is OpenBSN, and the other major one is called Contiki, which have support for many Nordic semiconductor chipsets and also other platforms. But Contiki is not really a versatile operating system due to the internal structures for the callback interface, threading model, etc. So what we did, we integrated the 2 subsystems running the Tish stack on Contiki on an NRF board, together with Espressence using the user space socket abstraction, which allowed us to connect the board using UART. We also tried this on the nRF53 series, but here we can actually run the Zephyr on the application CPU, so we don't need to have different SOCs to run both of the systems. And in that case, we have slip over the open AMP shared memory in Zephyr, which is similar to how you would run the thread stack on the 53 board. So waiting for this one to come up. I think we need to have the picture here.
You actually talk on your picture.
Yes. Okay, so we ended up with something looking like this. We have sensor nodes that will run a board with either the 52 series and NUTX presence, or we run on the 53 series with Zephyr, and they connect over the short-range radio to a border gateway, which consists of another board running short-range radio plus an instance of AWS Greengrass. And there we need to do a little bit of a protocol conversion, because the connections to the left is more suitable to use UDP-based protocols, versus Amazon requires TLS and MQTT, but that we can do in a conversion with a component called MQTT-SN, which is the UDP version of MQTT. So for the conclusions of this, we can see that both the 2.4 and sub-GHz can offer good link range. In optimal line of sight conditions, we can reach kilometer of range. However, in vegetation environments, the 2.4 is super restricted. You can easily be down to tens of meters if you are in crop for agricultural use cases. Here, then the mesh network can, of course, increase the range, and with the standard 1 to 17 schedule, we can have a duty cycling that allows devices to sleep for 95% of the time. The link bandwidth here with this scheduling then is probably in the range of 3 kilobits, less in larger networks, because the scheduling does not account for aggregated traffics from nodes in the sub-tree. And with radio at 10 milliamps and 95% sleep cycles, we are pretty confident that we can have a device that can run using energy harvesting. So looking at possible future integrations to have this more native into NUTX, we can look at the involved components here. There is support for 802.15.4 in NUTX, as I understand, but not for the TISH amendment. 6LoWPAN is already in NUTX. There is no RPL, and there is no scheduling, and there is no JP. And then the last item I put is the spinel, which is sort of the host control interface that is used by OpenThread to communicate between an application processor and a network processor or radio control processor. So I hope that can bring some inspiration for the community for continued work in this area, because I think that low power communication is pretty important for IoT applications. That's about it from me for today. Are there any questions?
Thank you, Peter. Quite nice presentation regarding the application of communication for IoT. And I especially liked your last slide. So if I'm allowed a question.
Yes.
Are there any plans to go deeper than just analyzing? Are there any plans on actually contributing something to the NATEX projects regarding this IoT communication?
I think the work with the user space socket implementation that can onboard the TISH network stack similar to the Wi-Fi, that is probably feasible. I mean, the work is done. I think it's just a matter of packaging and formal approval and things like that to do that. But then there are other possible work items that you can also think of.
Thank you. We have another question from the room.
It's more like a comment, not a question. First, that Contiki NG OS already includes all the RPL routing code, and it is very mature and it works. So we can get inspiration from that.
Well, I would say that it works. To say that it's mature, I'm not so sure. But you can definitely get the implementation, and for the actual protocol part that is the over-wire signaling, I would say that it's probably as close as the IETF specs that you can get, because they usually try things out in that platform before it gets standardized by IETF.
And the other is to achieve time-slotted channel hopping. This requires really tight timing and synchronization. So we will need some sort of hardware abstraction layers to support different radios that are like these discrete radios, like external chips like the CC1101. But we also need to support system on chips like the EFR32 from Silicon Labs. So we need to design some kind of hardware abstraction layers that supports this tightly timing of the time-slotted channel hopping. It is possible to do. I just raised the flag because it is not as simple as we might expect, but I am sure we can do it.
If you look at the IEEE specification, I believe that they have the sort of host control interface that will cover most of those topics. Then it's a matter of whether you want to implement it that way. The Contiki implementation does not follow the IETF interface at all. Yeah. They have their own way of doing it, more like callbacks for the different platforms. But it should be doable. I'm not sure if anyone has actually done it by the book that way. I don't know any other implementations of this rather than the OpenVSN and the Contiki. And it could be mentioned that there is a prototype integration of OpenVSN running in the Riot OS as a process. So we have the entire stack of the OpenVSN with the running into OpenVSN. I never got it to work on the 802 series, and apparently there was something wrong with the version of the 52 board that I was using, because I was involved in conversation with the Riot community, but we never got it to work. But that was also a sort of an interesting encapsulation to get the network stack packaged and running on your platform. Probably not the most efficient way to do it.
Many details.
Yeah.
Thank you.
Thank you very much. Do we have other questions?
Yeah, can you please read about the new audio? I think the audio from YouTube, YouTube not good.
Read where?
From Tommy. What's the maximum size of mesh network and how it can be extended when the limit is reached?
Okay, so the question is, what is the maximum size?
Yeah, size of the mesh network.
Of the mesh network, and how can it be reached?
And how it can extend it when the limit is reached. possible to route between different networks?
Between different mesh networks.
Network,
Yeah, you could if you consider that to be like a form of border routing, because eventually you will need to route your traffic from your network to external internet or maybe another mesh network. So that should be possible. For the maximum size, I think the theoretical size is thousands of nodes. But when we do, we haven't, of course, built a network that's size, but we have ran network simulators that can evaluate performance for a large number of nodes. And what we can see is that the signaling involved for the nodes to synchronize, to be scheduled, and also to exchange the routing information, that part is becoming more and more bottlenecked when you add hundreds of nodes. Also very much depending on the topology of your network. If you have a very optimal geographic placement of your nodes, you will have one performance. But if you have an unlucky topology and also switch on the nodes in an unlucky order, the network would have to be rebuilt in order to find the optimal routes. And when you reach more than 500 nodes, that is becoming very unstable according to our simulations. But we think that is also a matter of your density. How many nodes per area do you really need? I mean, if we can have hundreds of nodes and we can have a link range of hundreds of meters, you will have a substantial area coverage already there.
Second question. Actually, did you study or read or try it, the sidewalk from Amazon?
No, we have not in detail evaluated the Amazon sidewalk, but we we intended this to be as much as possible infrastructure-less. That is, that we were thinking of a deployment of a network that can be locally managed by harvesting and mesh technology, and then at some point we will have some sort of an unconstrained border gateway that could be maybe even non-terrestrial for cases where there is no connectivity available in your deployment site.
Thank you.
Thank you very much. If there are no other questions, I would like to thank you very much for the talk, and let's proceed to the next one.